Two-way tables and marginal distributions. So two-way tables, we're still talking categorical variables, but we're separating it by different things. Like in this case, I'm going to be rich, or maybe not. So a survey was taken of 4,826 randomly selected young adults aged 19 to 25. And they asked them, what do you think your chances are that you're going to have much more than a middle-class income at age 30? So here's the table of responses. So we've got a two-way table because we split this by gender. So there is a column variable, which splits it male and female. And there's a row variable, which splits it by opinion. So some people say you have almost no chance of being rich by age 30, some chance, but probably not, a 50-50 chance, a good chance, or almost certain, okay? There's confident people out there. So this is a two-way table because it describes two categorical variables, gender and opinion, about becoming rich. So a lot of times, the row totals and the column totals are missing. And so the first thing you need to do is calculate them. So sometimes they don't have this lovely column for you that says total, or this column here at the bottom, row I guess, that says total. So how would you find it? Well, this number is just the sum of all the females that responded to the survey. This would be the sum of all the males, right? The total here would be the sum going across 96 plus 98, the total number of people who said they have almost no chance of being rich. They don't believe in themselves. All right. So the distributions of opinion alone and gender alone are called marginal distributions because they appear at the right and bottom margins of the two-way table. So a little definition of what the heck marginal distribution is. So the marginal distribution of one of the categorical variables in a two-way table of counts is the distribution of values of that variable among all individuals described by the table. It's kind of a confusing definition, but you should write it down. All right. So here's an example of a problem you might be asked just looking at marginal distribution. So use the data in the two-way table to calculate the marginal distribution in percents of opinions. Make a graph to display the marginal distribution. Describe what you see. All right, so we're talking about opinions, and we are not separating by gender. So if you go back to this table, we want to separate out by opinions. In other words, what percent of all the people said almost no chance? 194 divided by 4826. And so that's what you would fill in for almost no chance. I already forgot what it was. 96 over 48, whatever it was. Okay? Something like that. And you get like whatever percentage that is, right? And then some chance. So you go back to your table. 712 over 4826. 712 over 4826. And you say the percentage of people who think they have some chance of being rich, etc., etc. You guys get that? All right. Then they're going to make a bar graph. On the bar graph, what would you guys put on your horizontal axis or your x-axis? Opinion or response. And what would you put on the y-axis? This would be percentages, because we just converted all of these to percents. So chances of being rich by age 30, and we've got most people kind of putting themselves in the 50-50 or the good chance category. Okay? And you make a lovely bar graph. So we're not going to do this problem. I just want to show you guys that what is missing from this table. Yep, the totals. So you would need to calculate the total going across as well as the total going down in order to find different marginal distributions that you might need. Okay? All right, relationships between categorical variables, conditional distributions. So marginal distributions tell us nothing about the relationship between the two variables, right? Because that marginal distribution just told us the total opinions. So to describe a relationship between two categorical variables, we must calculate some well-chosen percents from the counts. For example, let's say we want to study the opinions of just women, right? We just want to look at the females and how much they believe in themselves when they turn 30. So if I look at just the females, you want to isolate this entire column. Okay, so if I want to say the percentage of females who have almost no chance, what would I divide? Exactly, 96 by 2,367. All right, so I'm going to have to calculate this percentage, and then the next one, and the next one, the next one, the next one. So they did that for us right here. And we've got our majority of females and the 50-50 and the good chance here, they believe. All right. So go ahead and write this definition. This is called conditional distribution. So marginal was that total. Conditional is I want to look at something separate, like male-female. So a conditional distribution of a variable describes the values of that variable among individuals who have a specific value of another variable. There's a separate conditional distribution for each value of the other variable. Okay, so we just did the conditional distribution of opinion among the females. Same thing among the men. Again, just make sure that you go down this column here and divide 98 by, this time, 2459. So there's a different number total of males. So you use the total for the male column. And you get your percentages amongst the men. And we still have most people believing 50-50 and good chance. All right, so that's a conditional distribution for men. There is another way to go, which is across, you guys. So we could also examine the 5 conditional distributions of gender, one for each of the 5 opinions, by looking separately at the rows in the original table. For instance, the conditional distribution of gender among those who responded almost certain. So instead of going down, we can go across, and I'm going to look at just the almost certain people. Well, how many of those people who are almost no chance how many were female and how many were male? And so we would divide 96 by 194 and 98 by 194. And we would do that for all 5 opinions. So we're separating it out by opinion. So this first one calculates just that first one who said there's, or just the one that's almost certain. So 45% of females and 55% of males said they were almost certain to be rich by age 30. So you guys, which one's better? Well, it depends on what they're asking. So in this case, you guys, it seems more reasonable to think that gender might influence young adults' opinion about their chances of being rich rather than their opinion influencing gender. And so we would use probably the down columns the first way and see whether the data supports this idea. All right. So here's both. Putting it all together. Okay, they basically did it already for us, but we already talked about how to find the percents of females versus how to find the percents of males, and we can make what's called a side-by-side bar graph. All right, so this lovely graph, you guys, we've got our females in blue and our males in red, and so we have more females than males who don't believe in themselves, more females than males who don't believe in themselves, and when we get to these rich people who really believe they're going to be rich, there's more males than females. So that actually provides something interesting, right? So in stats, if there's something interesting to be found, that's usually where we're looking to separate out the data, all right? So based on the sample data, and you guys will have to write some sentences explaining, well, what did I gather from separating it out that way? So men seem somewhat more optimistic about their future income than women, right? And that's the only way we could figure that out was by doing these separately, conditional distributions, and making that lovely graph. That helped, all right? Men were less likely to say that they have some chance but probably not, and men were more likely to say that they have a good chance or are almost certain. to have much more than a middle class income by age 30 than women were. So use comparison words, more than, less than, things like that. Okay, this is just FYI that you could have used a segmented bar graph. This is basically all the females here, all the males here, and they just stacked the different opinions up to 100%, and then they color-coded it all over here. What's a better graph to use? Which one of these is easier to compare? The one we just looked at, the bar graph, or this one? Bar graph, right? Bar graph's definitely easier. This is like, you're like, I don't really get it because they're not lined up, you know, so it's kind of hard to compare, okay? All right, association is another important word for the day. So both graphs provide evidence of an association. So you'll be asked questions like, is there an association between gender and opinion about future wealth in this sample of young adults? And you would say, yes, there is an association. It seems like men believe in themselves a little bit more, according to this survey, okay? And so you would say yes. Here's the definition you might want to write in your notes for association. We say there is an association between two variables if knowing the value of one variable helps us predict the value of the other. I would just write the first sentence. The second sentence is the same thing in the negative. If knowing the value of one variable does not help you predict the value of the other, then there is no association, okay?